Welcome everyone to the second day of EAAMO and to the first keynote of the day given by Krishna B. Gummadi. I'm very excited to introduce Krishna. He's a scientific director at the Max Planck Institute for Software Systems and a professor at the University of Sauerland in Germany. His research interests are in the measurement, analysis, design, and evaluation of complex internet-scale systems, in particularly social computing systems. His work on fair machine learning, social online networks, and media internet access networks, as well as peer-to-peer system, has received numerous awards in the computer science community and is continuously inspiring in the space of normative questions regarding ethics and fairness of complex systems. It's my pleasure to introduce Krishna at today's keynote, and he'll be talking about fairness in multi-sided and multi-stakeholder online platforms. Krishna, if you'd like to share your screen and start. We can see your screen, by the way.
Thank you, Anna. Thank you for the kind introduction, and thanks everyone for both inviting me and for attending the talk. Today, I'm going to tell you about some of the challenges more than solutions that we faced when we try to tackle some issues related to fairness in multi-sided or multi-stakeholder online platforms. So let me get started. Oops. Oh, yes. So the sort of systems that I'm going to talk about today are human AI collaborative decision-making systems. And these are systems where you have increasingly algorithms assisting or nudging or overseeing human decisions. And these sorts of systems are increasingly pervading every aspect of our lives. For example, today you have risk prediction algorithms where assessment of where the next crime is likely to happen, or which employee is likely to leave, or which child is at a greater risk of injuring themselves, are essentially influencing human decisions. And similarly, there are numerous match and market making algorithms on gig economy platforms like Uber, Airbnb, and Kickstarter that are increasingly influencing how riders are essentially assigned to drivers, or how hosts meet travelers, and so on. And finally, you also have search recommender and reputational algorithms on sites like Google, Facebook, and Twitter that are increasingly mediating social discourse and influencing who we meet, what sort of news we see, and increasingly our whole worldview as well. Now, given the sort of impact these algorithms are having on our societal lives, it's only natural that there have been numerous concerns that arose over the past several years about their fairness. And these concerns are of a variety, are quite varied in nature. For example, there are concerns about discrimination in predictive risk analytics algorithms. So here, what I'm showing is a headline article from ProPublica that talks about machine bias, that there is a software used across the country to predict future criminals, and it is biased against minorities, and in this particular case, blacks. And the country that they're referring to is the US. And then there are concerns about opacity or lack of transparency about market-making algorithms. And here, again, I'm showing a headline from Wall Street Journal news article that was talking about how Amazon non-transparently changes search algorithms in ways that boosts its own products at the expense of its competitors. And finally, there have been numerous concerns raised about implicit biases in search and recommender systems. And here I'm showing an example of a New York Times article that was talking about how the German news viewers were being led by YouTube towards increasingly far extremist views of the articles. Now, in response to all these concerns, there has been a lot of work that has been kickstarted in the research community, and I would. And this is perhaps a bit of a caricature, and it's not a perfectly fair thing to say, but I would go out on a little bit on the limb and say that we have done a lot of work on fairness, on algorithmic fairness, but a whole bunch of it is largely motivated by the applications of risk assessments. There are numerous notions and very interesting notions of individual and group fairness that have been proposed in this context. there have been numerous operationalizations of these notions. That is, what I mean by operationalization is once you have a notion, how do you define a formal measure or objective that interprets what the notion is about? There has been a lot of work on algorithmic methods that have been proposed to achieve the desired objectives. But I would like to sort of contextualize this work by saying a lot of the time, many of these works are studying the problem from the perspective of a single side or one set of stakeholders. And that's often because in predictive risk assessment situations, oftentimes there is one set of stakeholders. And what I mean by this is, for example, if you take recidivism risk prediction, there is one set of stakeholders, which are the defendants, and you want to be fair in terms of your assessments across the defendants. But sometimes when you begin to go to multi-sided platforms, and what I mean by multi-sided platforms are platforms like gig economy platforms like Uber, where you have multiple stakeholders, like you have drivers, riders, and Uber platform itself. And then if you consider an e-commerce platform like Amazon, you have consumers, producers, sellers of the product, and then Amazon as a platform itself. And similarly, if you think of online conference scheduling platforms, you have the stakeholders are presenters and attendees. And finally, when you think about online charity platforms like donorschoose, you have different sets of stakeholders like donors and recipients. And the point that I would like to raise is that in these multi-sided or multi-stakeholder platforms, the fairness concerns become a lot more intriguing or interesting or complicated, whatever way you want to think about it. It's because your algorithm not only needs to be fair, for example, in the context of Uber, amongst all the drivers and amongst all the riders, but you would also have to trade off the beneficial outcomes for drivers with those of riders and vice versa. So in that sense, multi-stakeholder online platforms raise a lot more challenging fairness concerns. And those are the ones that I'm going to focus on in this talk. So my talk has two parts. In the first part, I'm going to talk about some work we did about a gig economy platform, which is ride-hailing platforms. This is a work that we published at KDD 2019, in case if you would like to look up for more details. And later on, I'm going to focus on an online donation platforms, which is donorschoose.org. So let's get started with the first part. So pretty much every one of you would have been familiar with ride-hailing platforms like Lyft or Uber, and what these platforms fundamentally do is they have algorithms that are matching drivers to passengers. It's this matching algorithm that we would like to focus on. Now, there have been numerous concerns raised about these platforms and concerns for the stakeholders in these platforms. So, for example, from the perspective of the riders, there are numerous concerns about the amount of waiting time or the surge pricing that riders are subjected to. And from the perspective of the drivers, there have been numerous concerns raised about whether they're able to earn a decent living wage when they are participating in these platforms. Now, to motivate some of the fairness concerns, I'm going to start with the data set that we gathered. This is an anonymized data set. It came from an Asian taxi riding platform. This is actually a platform where it's not a gig economy platform. It is a big taxi company that essentially was doing the task of ride distribution across 15,000 drivers, and there were over 4.6 million ride assignments that we analyzed as part of this. And in this particular situation, there are always more drivers than there are passengers requesting rides. So in that sense, this data set is one unique situation where you have a ride-hailing platform with always more drivers than there are ride requests.
Vous avez une
So, okay. So one of the first things that we did once we got the data was to actually analyze the distribution of the driver income. And here what I'm showing is essentially, for those of you who are familiar, it's a Lorenz curve. And what I'm showing in this graph along x-axis is the cumulative percentage of drivers. And along y-axis, what I'm showing is the percentage of income that they earned because out of the ride assignments in this data set. And so if every driver got an equal share of the revenue, then essentially the curve would follow the black dots. And any curve that is below this dotted black line, it suggests that there is an inequality in the income distribution. And so what this plot shows us is, if you looked at the top 20% of the most successful drivers, they are earning 40% of the total outcome. Oops, of the 40% of the total income. And if you look at the bottom 50% of the least successful drivers, they're earning about 27% of the total income. I'm sorry for the slide changes. I'm not really sure what is going on. Excuse me about that. So the bottom line is there is a significant inequality in the income that is earned. Now, at this point, some of you might be wondering, could it just be because of the amount of time that the drivers are available to drive on these platforms? And actually, that's not the case. And what I'm showing in this graph here is essentially that a similar pattern is observed even when you normalize the incomes of the drivers by the number of hours they were driving. So the blue dots show the income per active hours for drivers. And what you can see is a significant difference in the amount of earnings they're receiving because of the rides they were assigned. Now, this got us thinking about whether this is a more broader problem and whether we could think of a more fair ride-hailing algorithmic designs. And so to do this, let's start with a simple model of a ride-hailing platform. So we can think of essentially a time axis, and you have drivers available at different points of time, and then you have riders available at different points of time. And then essentially you could think of the ride-hailing platform as producing a sequence of matches between drivers and passengers over time. That's fundamentally what is going on. Now, what we thought we would model this as, to gain some traction on the problem, is to group passenger requests arriving within a short period of time. That is, we define epochs, and then we say you could think of essentially doing a matching between the requests that arrive within a period of time, like time in the epoch 1, epoch 2, and so on, with the drivers that are available during that epoch. So essentially, what you can view this problem as is one of repeated matchings. So in each epoch, you have a certain number of drivers that are available and certain number of requests that are coming. And then essentially what the ride-hailing algorithm is doing is essentially doing a matching. And you could think of this as one of like repeated matchings over time. Now, depending on the number of drivers or riders that are available, sometimes you will have a complete matching for the drivers, or sometimes you have complete matching for the riders. Like here, you have complete matching for the riders, and I guess here you have complete matching for the drivers in the second epoch. Now, the question is, then the next part of modeling is modeling some sort of a utility function for both sides. Now here, typical way to think about this would be that there is a taxi and it's at a certain distance. It's at a certain distance from the passenger who is requesting the ride. And then this passenger would want to get to a certain destination, and there is a certain distance here as well. So you could think of the utility for the passengers as the amount of time that they would spend waiting for the taxi to arrive, which could be captured by some negative function of the distance. And similarly, you could we could simply define utility for drivers as the effective distance that is traveled. And what we mean by effective distance is this is a distance for which they would get the fare, which is the distance that the passenger travels, minus the distance that they would have to travel to pick up the passenger in the first place. Now, these are just some simple utility functions. Of course, you could define a variety of different utility functions. Now, once you model the problem this way, the utilities naturally capture preferences. That means once you have a bunch of drivers and riders, essentially these utilities end up defining for each passenger what their preferred ordering of the drivers is. And for each driver, it also defines a preferred ordering over all the passengers. And now the advantage of modeling it this way is essentially now this boils down to a problem of how to fairly match preferences across both sides. And this sort of a mapping is useful because there is a long history of works on fair matching. And there are lots of interesting matching markets that have been studied, ranging from school admissions to kidney exchanges. But the one thing that the existing works do not consider is fairness of repeated matchings over time. So the real interesting question is, how do we think about fairness in these repeated matchings that is modeled by ride-hailing platforms? Now, once again, here, the idea is quite simple. And we thought, well, you could think of amortized parity. And what we mean by that is, in some sense, over time, you want to sum up the utilities of all drivers that they get in each of the epochs. And what you might want is the sum of the utilities across the different repeated matchings for the drivers to be equal. Now, of course, you could also have a slightly different notion that takes into account the amount of time that the drivers are active. And also you could take into account other sorts of additional features like the ratings of the drivers and the type of car that they're driving and so on. These are things that you could utilize, that you could incorporate in the definition of the utility function. And you can also define some similar notions of fairness for the passengers as well. Now, once we have this sort of a model, let's see how some naive methods that only consider the preferences for one side work compared to the ones that consider preferences for both sides. Let's start with some very simple methods that consider only one side. So, for example, if your algorithm is only considering the preferences for the drivers or preferences for the riders, you would pick the algorithm nearest driver first, which is you just assign each passenger to the nearest driver to them. The other way of thinking about the one-sided algorithm is you pick the driver who is worst off so far in terms of their utility. So this driver could be somewhere very far off. These two represent, in some sense, two extremes of algorithms where you're only considering the fairness from one side and you're ignoring the other side completely. Now, when you look at the performance of this NDF and WDF, what you notice is that the inequality in driver income, when you take the WDF, which considers the driver's perspective, it comes down to 0 compared to the inequality that exists before in the other side, in the nearest driver first. But there is a problem. While on the driver's front, the WDF does extremely well, its performance is really bad in terms of if you consider other factors, like from the perspective of the riders, in terms of the average waiting time for the riders. And here you see that the green and the orange curves completely swap. With WDF, the average waiting time can go significantly higher than with NDF, which is what you would expect as well. And because of the long waiting times, the overall system itself is less efficient, and the overall average monthly income across all the drivers also ends up decreasing. So the point is, just trying to think of this from a single side is potentially risky. So let's try out another idea, which is what if we took both sides together, right? And one way to take both sides into account is you define some sort of an inequality function over the utilities for the riders, for the drivers, and you define a inequality measure over the utilities received by the passengers. And then you put some weight lambda and 1 minus lambda. This is a tunable parameter to trade off between the inequalities in the utilities for both sides. Now, of course, then the interesting question is like, what sort of utility function would you define? Now, the temptation here we had was to start with some inequality indices that exist in the economics literature, but the problem is oftentimes they're very hard to solve for. So we went for a slightly simpler proxy for inequality, which is we tried to define inequality as the difference between the driver that has the maximum utility and any other driver. So you're comparing with the driver with the maximum utility or the passenger with the maximum utility, and you're trying to minimize the difference between these utilities. Now, I'll skip over the details, but you can at this point with these definitions, you can actually cast this as a problem, as an assignment problem, where the goal is to get the minimum cost one-sided perfect matching. The reason you have one-sided perfect matching is because the situation that we're considering is one where there are always more drivers. So you want to get the perfect matching, that is, every rider should get assigned a driver, but you want to have some minimum cost, which is shown above, which is just a formal way of representing what I mentioned on the previous slide. Now, it turns out that, of course, you could cast this as an integer linear programming problem, but in this particular case, you can actually have a solution with bounded complexity, because this is a well-studied problem in fair matching literature, and you can use the existing solutions. Now, let's quickly take a look at the resulting performance. Now, here, what I'm showing is the average monthly income that the drivers earn. This is the NDF and the WDF, which are the naive one-sided methods that I talked about before. And here I'm showing the results for various different values of lambda. And the high order takeaway is that when you try to simultaneously optimize for both sides, you can actually ensure higher average income for the drivers, while simultaneously keeping the inequality low. Low compared to the extreme one-sided algorithms. And similarly, if you look at the waiting times, you also get similar sorts of benefits with various different values of lambda. You can trade off the waiting time as well. So I'm going to quickly move over to the sort of open questions that we had after we did this work. We view this as a very, very preliminary work in this space. And there are a number of open questions. For example, we never studied the real world scenario where you actually have, there are times when drivers are more scarce than riders. And in fact, it can toggle, the scarcity can toggle from one side to the other side. And we haven't studied how well these sorts of algorithms would perform in those situations. And then there is a whole bunch of normative questions, which are very important. For example, there is a question of whether algorithms should try to compensate for poor location decisions made by drivers and riders. And what I mean by that is today, oftentimes drivers have strategies for locating their cars at particular places in the hopes of getting a better price or a quick ride request. Whereas here we're suggesting that algorithms compensate for that. And there is this question of, is it actually a better system designed to just to keep the matching algorithm simple and understandable and transparent, and let drivers and riders make the choices themselves? And then there is the other bigger question of when service requests when service requests and processing are distributed across space and time, are there some procedural fairness considerations? And what I mean by this, and the best way to explain this is, imagine how rides are assigned when you walk out of a train station or an airport. When all the drivers and riders are at the same location in space, then essentially queuing is a simple procedural way of procedurally fair way of assigning rides and riders to drivers. The longest driver gets the next ride, longest waiting driver gets the next ride, and the longest waiting rider gets the next ride. But the problem, of course, is when these riders and drivers are distributed over space, and then you have these requests coming at different points of time, it's not really clear how to compensate for it. And it raises some very interesting questions. So with that, I'm going to move on to very quickly to the second part, where I'm going to talk briefly about some work we started doing in the online donation platforms. And this is some work that we published at CSCW. Actually, this should be 20, not 19. So the topic for this is the focus is, we're going to focus on educational charities here. And the high level idea is that we're going to focus on public school funding in the US, which is widely accessible and free of charge, all the public schools. And the question is about the funding of these public schools. Today, they're funded by a combination of federal, state, and local taxes. Now, here, what I'm showing in this graph is the funding that schools receive from local sources. This is local property taxes. What I'm showing along x-axis are schools grouped based on the percentage of students that attend that school district that are from the poor families. So every school district gets a score based on the percentage of students attending the district that are from poor families, and we group them and we divided these into percentiles. So each point here represents one percentile of the distribution. And what I'm showing here is the distribution on the y-axis is the average per capita, that is per student funding that is given for over a year from the local sources. And as you can see, there is a wide range of there is a wide range of local funding here. And then here, this is often complemented by state and federal funding. And if you notice here, the state and the federal funding tries to compensate for the inequality in the local taxes. But at the same time, if you look at the y-axis, the scale of the y-axis, they're not able to completely compensate for the inequality in local taxes. So as a result, if you looked at the overall funding, there is still a significant inequality in per student funding that is that the schools receive in the US public schools receive. So given this inequality, there are often needs that are not met, and this has given rise to educational charities, and there are a variety of them that are increasingly becoming popular, like Digital Wish, Adopt a Classroom, and donorschoose. And in this talk, in the rest of the talk, I'm going to focus on donorschoose and what donorschoose. And I'm just showing you a screenshot that I took this morning from donorschoose, and what it shows is there are like 55,000 projects that are currently live, and essentially you have a variety of ways in which you could search for the project, and you could apply a variety of search filters, and there is information about how much donation is still needed. Now, the important or the interesting thing is that all donation requests on donorschoose are verified, and therefore there is no spam. You don't have to worry that something is actually a spam, because they verify that it's only teachers at these public schools that are allowed to post legitimate requests on these sites. And these sites have these donation requests are often organized like Kickstarter campaigns. There is a time frame before which you have to receive the requested donation, and if you don't, then essentially the request fails and it won't be funded if you don't receive the full funding. And the data set that we analyzed is from 2002 to 2016. This was a data set that donorschoose itself released. There was over $500 million donated to 1 million projects, posted by 70,000 schools and from 1,500 school districts. This is about 9% of all school districts. So 90% of the school districts are actually not represented on donorschoose. And that's an important thing to also remember. And on average, every year, there is about 70% success rate for these projects. Now, the key question that we were interested in is, are the donations on donorschoose at least going preferentially towards the poorer school districts? Because you would expect that at least that might be happening. And this is what we wanted to check. So the first thing we did was we looked at the number of requests that are being donation projects or requests that are being posted by schools with varying levels of poverty. And this poverty is once again being measured by percentage of students from poor families. And there are some well-defined thresholds for defining what constitutes a poor family. And what you notice is you do have more requests from overall poorer school districts. But the interesting thing is, if you look at the average amount per student that is being requested as part of these requests, it actually goes the other way. There is less funds requested per capita from poorer school districts. And the reason for this is the sum of the poorer school districts are significantly larger. And as a result, when you normalize for it, it goes lower. Then let's look at success rate and the amount received. Now, when you look at the average success rate, the interesting thing is overall, you have a similar sort of a success rate across the board. The success rate for projects varies between 70 to 75%. Now, on first glance, we thought this is great. It doesn't depend on the poverty level. But on second thought, you might wonder, is it actually good that the success rate is completely independent of poverty level? Is that what constitutes equitable donations, for the success rate to be completely independent of the poverty level? And then we also looked at the average donation that is received per student. And because even though the success rate is the same, because the per student amount that is requested is lower in the first place, as I showed on the previous slide, in general, if you look at the per capita flow of funds on donorschoose, you'd actually, the poorer school districts are per student receiving lesser amount, even on these online charity sites. And that's the point that I wanted to make. Now, there could be a number of reasons for this, including, I'm going to just skip over this slide in the interest of time, but including the fact that that sometimes the teachers from the richer school districts are more well connected, and they can actually ask their parent-teacher organizations to bootstrap the requests with funding. The thing that I actually wanted to focus on then is to understand, what we wanted to understand is to what extent are these donation requests or the donation or the flow of donations being influenced by the choice architecture on the site. And what I mean by choice architecture is essentially how the site is designed to make people choose what projects to fund. So for example, the search boxes can have a big impact. The search filters that that are being suggested can have a big impact. The default ranking can have a big impact. And then the way the project is being described, the project listing can have a big impact. And we wanted to understand to what extent these things are influencing it. So we had an experimental setup. And the way at a very high level the setup works is we recruited crowd workers to make donations. And the way we tried to, the way we studied it is we asked them to go through a proxy that we controlled. And what the proxy website was doing was it was intercepting the web pages from donorschoose on the fly, and we were changing the web pages. So the crowd workers are thinking that they're browsing the donorschoose.org, but we are changing them in ways with some treatments to see what impact redesigning the site might have on the decisions that the crowd workers would make to donate the money. Now, we gave each worker a virtual $100 to donate. And on average, a crowd worker took about 10 minutes, and we paid them $3 for doing the task. In addition, we gave them a $1 bonus, which we said that they could choose to donate a portion of that to the site in reality. And this is the portion that we actually donated to the donorschoose.org as well. And the reason why we did this is to make them actually feel involved in contributing some of their own bonus money that we're giving them to these things. Now, in terms of setup for the overt, we introduced two types of nudges. The first is an overt nudge. This is one where on every listing, the one here at the top left is the default one. And what we showed instead is the bottom right, where we explicitly highlight the poverty level of the school district from which the request is, or from the school from which the request is coming. And you can think of this as a conscious, as an overt nudge, because it can induce a conscious response. Similarly, we also set up a covert nudge. Sorry for the mistyping in the title. Here, what we just did was we changed the default ranking from most urgent to the highest economic need. And the expectation is that these sort of covert nudge might induce an unconscious response. Now, here is the high order experimental result, which I'm showing here in this graph. When the blue bars are showing the donation, we grouped all the schools into four categories: low poverty, moderate poverty, high poverty, and highest poverty. And the blue bars are the number of requests or projects that come from each of these groups. The green shows what would happen if people followed the traditional donorschoose.org design. The red shows what happens when we did an overt nudge, where we explicitly stated the poverty level on the project listing. And the purple one shows the default ranking, where we change the default ranking. Now, the high-level takeaway is that there is a significant difference. In fact, both the covert and the overt nudges that we introduced move the donations significantly towards schools that have higher poverty level. Now, we wanted to test whether people actually realize this. So we actually asked them at the end of the donation process, what actually influenced your choice of donations? And then, surprisingly for us, it turns out that when we provided explicit poverty information, many people said poverty level influenced their decisions. Whereas in the covert nudge, even though more of the donations went for the ones which are poorer districts, they actually didn't recognize it. So in other words, what happened here is in an overt nudge, people were overestimating the impact of the treatment, and in a covert nudge, they were underestimating the impact of the treatment, even though they were subconsciously transferring even more of their donations towards the poorer school districts. In the interest of time, I'm going to stop here because I'm sorry for running a little bit over time. I do have some open questions, but I guess I'll bring this up in the panel, and I don't want to take the time away from Ashish's talk. I guess we started a little late, so I'll stop here.
Thank you so much, Krishna. This was super interesting. I have one question to start with, which is just, I'm wondering, what kind of nudges, did you try different kind of nudges? Which are the ones that you found to be like helpful, or is there some sort of like diversity nudging concepts that you thought about?
Yes. So these are things that I could bring this up in the panel discussion afterwards as well. On the donorschoose.org sites, there are a variety of nudges that you could use. Like, for example, you could change the matching donations. That's another form of nudge. There is a nudge for how close the project is to completion. And that could be a form of nudge and so on. So in this particular experiment that we did, we primarily tried two nudges, the covert and the overt nudge that I was mentioning. But this is in fact what I find very fascinating. There's so many different types of nudges that you could use that it raises a lot of open questions as to what should be the goals of that nudging as well.